In Chapter 18, we will go over electrophilic aromatic substitution as well as reactions at the substituents on a benzene ring. Let's begin right away with electrophilic aromatic substitution. As the name implies, a substitution reaction takes place here, not an addition, but a substitution reaction. And usually this is shortened with EAS. So EAS stands for electrophilic aromatic substitution. You need an electrophile. You need an aromatic compound, benzene, for example. And of course, you need to replace an atom in the benzene ring, such as hydrogen, with the electrophile. So let's begin right away. This is the summary for electrophilic aromatic substitution reactions. Each is going to have variations in its mechanism, but in the second and third step, as you will notice, the process is pretty much the same. In the first step, it's going to change where you're making an electrophile. Of course, we have different substances here, but in the second and third steps, they usually follow the same pattern. So let's begin. If you would like to halogenate the benzene ring, X, which is either Br2 or Cl2, then you can add X, replacing a hydrogen. So there's a hydrogen here. That's what's being replaced. Nitration, meaning you're adding a nitro group. NO2. Sulfonation, adding the SO3 group. Friedel-Crafts alkylation, you're adding an R group. So methyl, ethyl, etc., propyl. So that's R right there. And of course, acylation is you're adding an acyl group, which is the RC double bond O. So that's what's happening. And we will go into each mechanism to show you what exactly happens in there. So quickly, going back, recall from your alkene chapter, that was chapter 10 from organic chemistry 1. This reaction took place if you added a bromine, and it was a very quick reaction. So you're adding benzene you're adding bromine, along the double bond here, and you would get the following. So this was the product, is you had an anti-addition of bromine to the double bond in the alkene. So this was an alkene. Now, if you attempt to do the same with aromatic systems such as benzene, the reaction is not going to take place at all. So for example, if you attempt to do this and you are successful, you would add bromine along this. So I'll tell you from now, the reaction is not going to take place, no reaction, for a very simple reason. The very simple reason is you lost aromaticity. And that's frowned upon so far. So let's go ahead and start with the first reaction. So how would you add the bromine then? You can, but you need what we call a Lewis acid. So iron 3 bromide is a Lewis acid. And of course, it can work with Cl2 and FeCl3, in case you're wondering about whether these take place. So if we just look at bromine, you would get bromine added like that. Only one bromine. It's a substitution. You're substituting that for, let's say, the hydrogen right there. Very well. So how the step one is the one that takes a different approach than, let's say, step 2 and step 3, because you're making, like I said, a different electrophile for every reaction in electrophilic aromatic substitution. So let's begin with the first step. The first step is when you place bromine, and bromine is a diatomic element. In the presence of iron 3 bromide, which is a Lewis acid. It means it has an empty shell. Means it can take electrons as a Lewis acid and electron pair. So what happens is that the reaction takes place this way, where bromine attacks the iron atom, forming a bond. Okay. At this point, if we were to put our formal charges, the bromine in the middle would have a plus, and then the iron would be a minus. So what happens is that this bond right here is a weakened bond. We say it's polarized. Polarized, you can see the different charges, or the charge on this bromine. No bromine wants to have two bonds, so one has to break. And this one is going to break, making this bromine electrophilic. So again, this is a weakened polarized bond. So let's go now to step 2. Step 2 of the reaction involves now the reaction between the benzene ring and the electrophile that you made from the step before, from step 1. So let's bring our benzene ring down here. And our electrophile. If you recall, there's a name we shared in Organic 1 for the product of an acid, a Lewis acid base reaction. That's called an adduct. So this is the adduct right here. So the reaction is going to take place by attacking the bromine, and this bond has to break. Okay, let me just bring this one down because I need to draw Lewis structures for the bromine and the bromine as well, bromine and the iron 3 bromide, as well as different resonance structures. Okay, so be sure that you place the H, because remember there's an H here. There's an H on every single atom, the octet rule on benzene. Make sure you have that visible because you will need it in the third step. And sometimes you may opt to choose it from the other carbon, and you end up actually doing the wrong transformation. It's not going to take place. So we know that this is in resonance. Should be a pro at drawing resonance structures by now. You're moving, once again, the double bond, and then the positive is now right there. There's another resonance structure. You should probably pause and see if you can draw the last resonance structure. Okay, so that would be moving. Is it? Oh, we're saying. Positive is right there. Very good. So remember, this is in resonance as you're moving the positive charge around. Remember, all of those are in one structure. So this is, we have the hybrid. So this right here is resonance stabilized. Carbocations. Carbocations love to have resonance because, again, they don't keep the positive in one place. So how would you then regenerate the aromatic ring? So I'm going to go with what your book has, although it can vary, but we'll just be consistent. So you're going to choose one of these resonance structures. So that's the idea. I'm talking about either the first one or the last one. The one in the middle, that H is a bit far. It's far from where the positive is. So you can either choose the first one or the last one. I'll just choose the first one. So we have let me just modify this a bit so that we can. Now you need a base here, and you do have a base. So your book has this step, which I agree with. I think it's more appropriate than having the bromine dissociate, but the negative on this. So what's going to happen is the bromine is not going to attack from these lone pairs, but actually the bonding pairs. So it's going to attack the H. This pair right here is moving to form a bond between the bromine and the hydrogen electrons between them and the carbon, they shift and they reform the benzene ring, aromatic. So here's your product, of course, plus HBr, that's what we formed, and of course FeBr3. So that's a catalyst. Remember, a catalyst does not get used up. You actually get it back at the end. Not sure about you reusing it, but that's the idea. This reaction right here is an E1 elimination reaction, if you recall from organic 1. E1 elimination reaction. So what you're going to see in the next few mechanisms is that the first step is going to be different. The next step, similar, meaning the attack is going to take place on the electrophile, but you have a different one. You're going to have, again, these resonance structures because it's resonance stabilized, carbocations. And then, of course, the last step is the base attacking hydrogen, reforming the aromatic compound. So again, we're back to aromaticity, I'm going to say restored.